Hello everyone. In this video, we will learn how to find derivative of y with respect to x when x and y are defined using parametric equations. Okay, so in other words, set x to be a function of a variable t, y a function of variable t. Then the first thing that comes to your mind is that the derivative of x with respect to the variable or parameter t, this is f prime at t, or dy dt is g prime at t. There is even more important or interesting function or derivative to find. What about dy dx? Just get rid of t and just find dy dx. First thing, you may say that why on earth that is important? Well, just simply consider the parametric curve defined by these equations, and then at some point I or someone else or you yourself we are interested in finding the tangent line to that curve at that point. And from the calculus 1 we know that the slope of tangent line can be defined by the limit of the difference of y to differences of x as x goes to 0. With a little bit careful work, you can make sense of this limit, and basically what we mean by dy dx, or derivative of y with respect to x, it really means this thing. Okay. Now, how to find it? Well, one way is that you go and eliminate t, and then you have a function y as a function of x and differentiate. That's the easy way. But in general, eliminating t is not possible. It's not easy to do. So we want to have a formula that no matter if we can eliminate t or not, we can differentiate. You may say that, okay, let's see what will happen if we can eliminate t. If t can be eliminated. In other words, I can write y as function of x. And well, what does that mean? Then it means that y, that if you plug in the parametric equation for x into that function instead of x itself, this will be the parametric equation for y. Yes. And well, if this is the case, we really mean dy dx is the derivative of that guy. But on the other hand, you see that if I differentiate both sides with respect to t, this will get closer to derivative of f. That's what we are interested in. This guy is dy dt, and by chain rule, I will have f prime derivative of the outer one times the derivative of the inner one. Okay, and well, voila, we have it there. So if I have if I write f prime, by the way, f prime I know that is dy dx, I can divide this thing to the other side. This is going to be dy dt, which is a function of t, divided by dx dt. This will give us the formula. You see that this part is easy to do. This part is easy to do. And then you divide them. That will give you dy dt. So this is just part of proof of the theorem when we can eliminate t. In general, you can prove the same result, and I'm not going to go over that, and use just this one as the formula for us. So when someone gives you parametric equations and asks you to find dy dx, you find the derivative of the upper one y with respect to parameter, and then divided by the derivative of the x with respect to parameter. Let's see this in some examples. Find the slope of the tangent line to the curve. This it's interesting to see what is this curve. I suggest that you try to sketch this curve, and it says that when t is equal to pi over 4. So when t is pi over 4, then our x is going to be pi over 4 cosine of pi over 4, and our y is going to be pi over 4 sine of pi over 4. This is just pi over 4 root 2 over 2. This is the same. Oh, yeah. This is pi over 4. Sine of pi over 4 is root 2 over 2. So the point of the tangent, the point at which the tangent line will touch the curve, it has a root 2 pi over 8 and pi root 2 over 8. That's the point. Now, for slope, we need to find dy dx, not dt, at that point. Well, I know that I can find dy dt and then divided by dx dt, the derivative of y with respect to t divided by derivative of x with respect to t, and that will give me whatever I want. Okay, so here the derivative of y is sine t plus t cosine t, and the derivative down there is cosine t plus minus, because the derivative of cosine is negative sine, and that will give me, I'm using product. Okay, now here's the important thing. When you use that formula, the result is going to be in terms of t. Now that point is obtained when you set t equal to pi over 4. Now I bring that pi over 4 and plug t equal to pi over 4 for getting that slope. So slope now is going to be sine of pi over 4 plus pi over 4 cosine of pi over 4, cosine of pi over 4 minus pi over 4 sine of pi over 4. Okay, so let me push that example a little bit lower, and while the values here are all known, root 2 over 2 plus pi over 4 times root 2 over 2, root 2 over 2 minus pi over 4 root 2 over 2. You can factor out root 2 over 2s from numerator and denominator and simplify them. We can go one more step, find the common denominator 4 in both numerator and denominator and cancel them, and this will give me the slope. Now I have a slope. Then to find the point, the equation for the tangent line, I need to use y minus y0 m times x minus x0. This is x0, that's the point of the tangent point, and this is y0. So that will imply y minus pi root 2 over 8 equals to 4 plus pi over 4 minus pi times x minus pi root 2 over 8. I can simplify that, but I don't see any point here to simplify. That is an equation for a line, and that's our tangent line. Let's do another example. Locate any critical points on the parametric curve defined by this guy. Well, recall the critical points are where dy dx either not defined or it is equal to 0. So we have to first find what is dy dx. Okay, so this means that we have to find the derivative of y with respect to t, derivative of x with respect to t, and here is 2t plus 2, that's derivative of y with respect to t, and down there is 3t squared minus 6. This is derivative in terms of t, and we know that the derivative is not defined. For any t you plug in there, it is defined, and unless the denominator, values of t for which the denominator is 0. So if this guy is equal to 0, then that the derivative or that expression doesn't make sense, and that means that t2 is equal to 2. T is either plus or minus root 2. So for t equal to plus or minus root 2, the tangent line, the dy dx is not defined. And the points that dy dx is equal to 0. So this guy is 0, means that the numerator is 0, and that means that t must be negative 1. So for three values, t equal to plus root 2, minus root 2, and t equal to negative 1, we have critical points. Now we have to find what are the x component and y component of these guys. So for t equal to root 2, the points are going, I'm plugging x here, so it will be root 2 to the power 3, which is root 8, minus 6 times root 2. How about y? This is just 2 plus 2 root 2 plus 1. How about t equal to negative root 2? This is minus root 8 minus or plus 6 root 2, and this is 2 minus 2 root 2 plus 1. How about t equal to negative 1? For t equal to negative 1, I have 1 cube minus 6, which is minus 5, and 1 plus 2 plus, oh, it is negative 1. Sorry, guys. This should be, t is negative 1 here. Yes. So I plug negative 1 there. That will give me positive 5. And if I plug it in here, it's going to be 2 minus 2, which will be just 0. So I have 3 critical points for that parametric curve.